Hi, welcome back to the lectures on GPU architectures and programming. So, in the previous lectures we have been discussing certain GPU optimizations, GPU based parallel program optimizations like reduction, like fusion, and we will now start with our last discussion on program optimizations in GPU, more specifically CUDA based program optimizations, and this would be the idea of thread coarsening. So, speaking in layman's terms, so when we are doing parallel execution of threads, they sometimes require to do redundant memory accesses, and also we require to do some redundant calculations, and also we often launch multiple threads, and the threads are pretty much lightweight, and launching so many threads in such cases do not make sense, because launching a thread also means creating a thread's context for the in the hardware, and keeping track of that thread, and if for that thread I don't really have too much of activity, then simply the launch overhead of the thread doesn't make sense, right. So, the idea of thread coarsening is that you do some kind of load balancing. That means you launch significant number of threads, but also make every thread bear some cost. That means make every thread do some meaningful activity, and so that the threads and also the threads should make reuse of results and avoid redundant work. I mean, what we mean here is, when we are doing a GPU based computation, every thread has got its own per thread private local memory. Every thread gets its part of share in the register file, right. So, these are things which we have discussed earlier also, like whenever you are using let's say you are using an NVIDIA GPU. So, I mean, while you can actually set that statically that what should be whether you are going to allow register spilling or such things to happen or not. I mean, by default they are prevented. So, when you are going to launch your kernel, the system is automatically assigning a set of registers for per thread activity, right. And that would also mean when a thread is doing its computation, the results are available in the registers which are fixed for that thread, but those are also the registers which a concurrently running thread cannot see, right. It is doing, maybe it is doing some activity for which this is not available, but it may be the case that these adjoining threads, I mean, they have some locality in terms of computation. They do some activity which could have been reused. So, if I make one thread to do the activity in this case for both threads together, then maybe some computation which the thread 1 has made can be used again by thread 1 if it is doing thread 2's activity without the original thread 2 duplicating the same activity inside its own set of registers or the set of registers that have been allocated to it, right. So, in that way, I mean, we will make these things clear, that how this reuse of results can happen and all that, and how I can make threads avoid redundant work. So, the concept is quite similar to loop unrolling, but here instead of applying it on sequential execution of a thread and avoiding multiple executions of the loop, we are actually applying it across parallel threads rather than on the serial loop iterations of a single thread. Now, of course, one important point we have to understand is that thread coarsening would result in a reduction in parallelism, but there are good effects of that also. That first of all, why does it result in reduction in parallelism? Because if I let one thread do the job of multiple threads, then my thread block size can decrease, or I can keep the thread block size same, but the overall activity can be done by a lesser number of blocks. So, if the total number of threads I launched is less than the number of threads that the GPU can execute concurrently, then there would be a reduction also in parallelism. But otherwise, what can happen is, if the original threads were very lightweight, now each of the threads have got some significant activity. So, anyway, if there is available parallelism, then the kernels would be launched and all the parallel execution units will be engaged, right. So, the beneficial effects, if we can summarize, is that the coarsening would require only less number of threads to be launched. So due to that, as we said, that lot of redundant execution can be minimized. For example, if there are barriers per thread, now since I have less number of threads in total, the number of barrier execution is reduced. So that would also mean an overall gain in the end-to-end execution time of the kernel. And since now I have more number of instructions to execute per thread, so that would also mean that now I can exploit hardware level instruction level parallelism, which were maybe earlier for each of the threads being very lightweight, there may not be too much parallelism inside the threads. Now this may also at certain points be detrimental. Of course, here we are just giving some placeholder definitions, like we have said that okay, the threads since the threads have own local share of register file, there may be redundant computation going on if threads are lightweight. So if we merge activities of threads to a single thread, then whatever was the computation by thread 1, and earlier it was done, maybe sometimes it could have, it was the thread 2 was unable to reuse it, but since now one thread is doing the job of 2 parallel threads, it can make a better use of the register file. So those were the arguments that we are trying to make in terms of thread coarsening's advantages. At the same time, if we try too much of that, it can also be disadvantageous. Why? Because suppose I am now coarsening the threads, making each thread do lot of activity. So then observe, this is the most important point here, that when the program is getting compiled, the compiler is figuring out the per thread activity and it's allocating a part of the runtime system. The runtime system is going to allocate a significant amount of part of the register file now to per thread, right? So that is a finite resource. The register file in totality is a finite resource. The shared memory in totality is a finite resource. So when the runtime system is going to allocate it, it's figuring out that okay, now the per thread register file usage has increased, right? Or the per block share memory usage has increased. So since the resource increase per thread and per block in effect has increased, the total number of threads that the system, or more specifically per streaming multiprocessor can execute will be reduced, right? Now this is a notion that is known as occupancy. So occupancy is the ratio of number of active threads per SM and maximum number of active threads allowed per SM. So let's say we have the number of maximum threads that are allowed per SM is 2048. That's the thread let's say that's the maximum thread context that I can have. And then it's not required that the occupancy that the SM will support in the runtime is same as that maximum limit. Why? Because as we have figured out that whenever I am launching the threads will be allocated local resources in terms of register file, the blocks will be allocated local resources in terms of shared memory. If I coarsen the threads, there will be a point that these values will be significantly high, that is the per thread resource requirement is high. The hardware in that case will not really launch that number of blocks into the SM as is allowed for the SM, simply because that many number of thread blocks cannot execute parallelly, because a lesser number, a subset of them is good enough to completely engage the local shared memory and the register file resources, right? So that would eventually result in a reduced occupancy value. This is a finer point, but I hope it is clear. We need to understand the SM can run as many threads that as there are SPs and SFUs there, right? And as many thread contexts that the SM can remember. But at the same time, when it is running the threads will be occupying its own share of local resources, right? So once I increase that share of local resources, the hardware will not really run that many active threads which it can, and this ratio is the occupancy factor. If I coarsen the threads too much, the occupancy factor is going to decrease, right? So that's the effect that the kernel's increased resource consumption will create in terms of occupancy, and that may be detrimental with respect to the overall kernel's execution. And the second thing is that if we are coarsening the threads or increasing the per thread activity, as we have discussed earlier, that with per thread activity increase, I may be removing some redundancy in terms of thread computation, right? Because earlier two threads were not able to share their computations in terms of registers value, I mean computed value stored in registers, but now they can. But at the same time, I am increasing cache activity, right? This would increase the cache pressure on the kernel, and that is also a resource, right? Now, at this point, I will like to also talk about something like with respect to cache that is present in the kernel. Earlier, we have discussed that for in the GPUs we have L1 and L2 cache. L2 is unified and L1 is present inside the SM as a shared memory plus L1 setting, which can be configured, right? Now, while that's true up to the Kepler class of architecture, from Maxwell architecture there are instances of GPUs with separate shared and L1 caches, right? So, when the threads are going to do memory reads and writes, they are also consuming the resource that's cache, and with per thread memory reads and writes increasing, the cache pressure also increases, and that also plays a role in deciding what is the total speed up gained by thread coarsening. And with it too much of coarsening, there may be increased cache pressure, there may be increased latency of the instruction execution due to this cache pressure, and that would be a detrimental effect, and it may finally lead to a loss of speed up. So, the point we are trying to make here is, for every kernel, it is not the case that you keep on coarsening the threads, reducing the number of threads as much as you want, and because if I think in a naive way, if I give more activity per thread, well, then I have then I would have less number of I mean, I am doing more amount of work per thread. So, I am really reducing the total grid size for the kernel, but that may not always be the case, as we are finding that there is a sweet spot with respect to what is a good coarsening factor. The optimal coarsening factor should be such that it will make maximal use of the GPU's parallelism. We have to understand that the parallelism is in length and breadth, right? Because I have a set of resources, I want to execute these resources in I want to consume these resources, that is the execution resources and the memory resources, as much as possible in parallel, but also in length, right? Because I want to use them as much as possible in parallel for as much time as possible, right? So, there is this sweet spot in parallelism. So, if we go too much with respect to coarsening, then finally it will lead to sequential execution and we will lose parallelism. So, this sweet spot is something that as a programmer you have to understand by looking at the activities in the algorithm. So, let us start with some simple examples of coarsening, and we will get back to this issue of speed up that one can achieve with coarsening later on. So, first let us start without coarsening code. So, on the left hand side we have the code which is without coarsening. So, as you can see, it is a simple program which is just checking whether which is just revealing what is the global thread ID, and then for the content in that the memory location for that thread ID, we are just executing a square operation. All we do with the coarsened version of the kernel is that make every thread do that operation for 2 consecutive locations. So, the initial case is you launch threads and they all perform a squaring of the data, and then in the modified version, so this is the without coarsening case. So, this is how with half the threads we are doing the activity, And as you can see that first we find the global ID, and we use this global ID, we just multiply it to create the offset at which it will work, because we know that now for all the previous thread IDs have worked on the two data points. So we have to then bring in this multiplication factor by 2 and the next element. So multiply by 2 and plus 1. So these are two consecutive locations, right? So for anywhere in between, you take the thread ID, compute the global ID, and then go to the next consecutive location. So these are the two consecutive locations for which we are going to do the work. So if we just make a small outline of the technique, what we are doing is we are merging multiple threads so that each resulting thread calculates multiple output elements, right? So they perform the redundant work once. So why shall we really say that? For essentially you can see that each thread, earlier every thread would have some launch overhead, right? And they will do this computation. Now we have reduced the number of thread contexts by 2, so that removes the overhead, and we have given significant activity for each of the threads. So for example, we can just say that when this has been fetched, the other data is also being used, is being computed in parallel by using some other, some is getting computed in another register by the same thread. So the work of loading the data is being reduced, and the results are getting saved into the register, and use the register results to calculate multiple output elements. While that is not that is not exemplified here, but it's easy to understand that when we have the threads, multiple threads merged, then suppose each thread was having some initial activity. Now I can do the initial activity in together, right? So let's say the initial, each of the threads had some common multiplication or some common constant evaluation to do. Now that is not specific to a thread ID or data or corresponding data space. If that is the case, so then that is the definition of the redundant work, and now that would be done in a smaller number of times. So that's point 1. Second point is intermediate results can be saved to the registers, and they can be reused for doing some computation for the which was originally done by the other threads. And then the register results can be used to calculate multiple output elements. Maybe let us consider the situation that earlier there was some per thread activity, right? And finally this per thread activities, the outputs which were computed by each of the threads, were going to go through some transformation, right? Now since two adjoining elements are already computed by a single thread, if that transformation was associative, then some part of it can be done right here. I hope that is I am making sense here. Suppose in the original kernel, whatever are the outputs, they are going to be computed. So let's say this is the final output of all the threads here. They are going to go through some transformation function f, right? So let's say these values are a1, a2, an. So I am going to apply f on a1, and then on a2, and then like that up to an. But now, so that many operations are required, but now inside this function only I can compute f a1, a2, and similarly I will, when these threads get done, then this job is, some of it is already done here, right? So at the final level I have to work with half of the values, right? Considering this is an associative operation, this is fine here, right? So just because each of the threads are now working on more data points, I am again making a lot of savings here with respect to achieving some more parallelism right at the thread level before the synchronization point. So we can understand that fundamentally what is happening, since I am increasing the per thread activity, I can reduce the redundant work which each thread was doing as a common activity. I can make use of the more number of registers to store intermediate values which can be used, and which can actually help me to calculate a final output value, which can actually help me to reduce a final step which the threads are supposed to do once they each of them compute their output value and then synchronize and then perform. Now some of that value, if that's an associative operation, some of that can be performed right now when the threads are executing on different data points. So the point we are trying to make here is also that the merged kernel code will use more registers, right? Now what is the issue here? That this may reduce the number of threads allowed on single SM, like we are speaking earlier. This may reduce the occupancy, right? Now increased efficiency that we are getting may outweigh the reduced parallelism for a given hardware. So this is an important point. Reducing occupancy is not the bad thing, right? So I may have a reduced number of threads on the single SM, but since I am also having fine-grained parallelism inside each of the threads, I am having a reduction in the local computations of the threads due to lack of redundant activity. I am gaining by doing some parallel computation on the outputs computed by the original threads now due to the quotient activity. Initially, the reduction in occupancy of the SM may not hurt because it may lead to more efficiency, right? So again, I will repeat this part. Each thread is consuming more local resources. Due to that, up to some point, it doesn't hurt because although they are consuming more resources, the SMs are full where they are going to operate with the maximum number of threads they are allowed. After that point, they will go to, if I quotient more, then the SMs will execute a lesser number of threads than they are allowed to execute, but still this reduced parallelism may not be bad enough because in spite of the reduced parallelism inside each thread, I am now exploiting some instruction level parallelism and I am doing some redundant work less amount of time. But after some point of time, it will start hurting the global execution view. So up to some quotienting factor, I may have increased efficiency even with reduced occupancy, but beyond the quotienting factor, the occupancy will go so much down that the reduced parallelism's disadvantage will outweigh the effect of increased efficiency due to thread quotienting. So again, I will repeat, up to some point, the efficiency factor in terms of quotienting that we gain in terms of efficient execution outweighs the reduced parallelism, but after that point, it starts hurting. If we lost too much parallelism, then it will start hurting. So again, to summarize, that up to some point, if you quotient the threads, you may not lose occupancy because still the SMs is able to execute threads up to its maximal limit. After some point, it will have reduced occupancy, reduced parallelism, but still the instruction level parallelism and increased efficiency will outweigh the reduction in parallelism. But again, after some point, the occupancy reduction is so high that quotienting will be detrimental. So something important here that with thread quotienting, the computation of the merged threads start sharing registers. This is something we have discussed earlier also multiple times. So why is this a good thing? First of all, as we all know that register file is extremely fast, right? So if I increase pass thread activity without decreasing the occupancy significantly, then still it's a good thing because if every thread brings more data and loads into its path thread available register file, then the threads, while doing their local computation, they reduce execution of memory access instructions, right? And in that way, they gain in high throughput, and and this is a good thing because earlier when the threads were not quotient, each of the register file portions that were available to each of the threads at the lower granularity, they are private, right? And threads, suppose the thread 1 gets a set S1 of registers available to it, thread 2 gets a set S2 of registers available to it. So they cannot share the computation results, right? Because they are private to their threads. But now when I quotient the threads, that set of available registers may be S1 plus S2. So the threads get more registers to work with, and now they can share the intermediate results. They can decrease the number of memory access instructions in between. Why? because now when the suppose earlier when some register was doing some storing some local result, and then for per thread activity maybe the register size was not good enough, that is register spilling, by default it would be deactivated in the GPU. So then there will be some access to the local memory, right? Sorry, access to the global memory. Memory access instructions will be executing, right? But now if I have more number of registers available, it may happen that due to this sharing of construct registers, I have less number of accesses required. I can avoid the register spilling a bit, and I mean, since the threads are able to share the computation results, so they will make a more efficient utilization of the larger set of registers that would be available to them, right? And that will actually lead to the efficient computation that we have been discussing in the previous slide. So the other thing is when we coarsen the threads, there has to be a choice of coarsening factor. So if we look into the example we gave in terms of the program, so this is simply a coarsening factor of 2. We are employing a coarsening factor of 2. You are increasing the per thread activity by 2, right? So what is a good coarsening factor is also an important issue. The definition of coarsening factor is it is the number of times the body of the thread is replicated. In that example, the replication is twice. Which coarsening factor gives the better performance, the best performance, to be precise, it depends on the program and the hardware. Coarsening factor for any problem in the hardware can be decided in 2 ways. I mean, we can get an estimate of the coarsening factor by performing a static analysis of the program, and the dynamic way would be to profile the program, you run the program with different possible coarsening factors, and also for each run you try different possible inputs of the program, and you get the execution statistics and figure out, okay, for what is a good coarsening decision for this kernel, right? So just to summarize here, let's understand that for each thread which we increase the per thread activity, per thread memory requirement, threads start sharing registers. In that case, they can store intermediate results inside the available registers. This may reduce memory access for the global memory, because if it can make a good use of the larger set of registers which are now available to it for sharing purpose, right? And that would actually ensure shorter latency for the memory accesses, because you have more data in the registers, and you execute, if you do not require memory access instructions, then you can attain high throughput in terms of the overall kernel's execution. So this is the advantage. We are not going too deep here. In the next lecture we will take some more examples. When we really take we will see that how the coarsening factor affects the kernel's execution. With this we will end this lecture. Thank you.